Let's get started with 5.3 exponential functions. Some of our learning objectives are to evaluate exponential functions, to graph the exponential functions that we're studying. We're going to look at this number e. It sounds weird, but just like we have pi, we have this number e that's really super important. We're going to talk about that. And then solving exponential equations. This section 5.3 is all about exponential functions, using exponents, really digging deep into those exponent ideas that we've seen before. So, to get started, I would highly suggest you review exponents and all the rules that go with exponents. We're going to be using them a lot in this class, and this is just the beginning. So go ahead and get your brains in the right place where multiplication rule, where we have our bases the same and our exponents here, we would add those together. Same thing with division. When our bases are the same and we have an exponent, we could subtract those things. The power rule, we have a power of a power. I call that the pow-pow. So the way I remember that is pow, pow, multiply now. Multiply now. Because if I have a power raised to another power, then I'm going to multiply them. So that's just how I remember it. The power of a product rule. So if we have a product being raised to a power, then we can give each one of those bases the exponent. Same thing with fractions. If we have a fraction raised to an exponent, each one of those guys can get that fraction. Zero exponent, probably a favorite. If anything is raised to a zero, it equals 1. The negative exponent, super important. Whenever we have a negative exponent, it's going to flip that base to the bottom of a fraction. And then if we have a fractional exponent, that gives us those roots. So if, for example, I had something raised to 1/2 power, that's taking the square root of that thing. But we can do it for any exponent fraction. So another example would be if I had it raised to a 3/2 power. Oh, that's not it. If I had it raised to a 3/2 power, then not only would it be a square root, but it would be cubed on the inside. So if you need to review these things, it would be a very good idea before you jump into this chapter to just review and make sure that you remember all of those exponent rules. The first thing we're going to start with is just evaluating them. So our first objective is to evaluate exponential functions. Let's look at some and get familiar with typing them into our calculator. That's really the big goal here. I see I have a base of 3. That's called our base because it holds up the exponent, and we have our exponent up here. Exponent of 2.133. If you already know how to put these in your calculator, that's awesome. If you don't, then that's what we're going to work with today. So I'm pulling up my graphing calculator here. I'm going to type in the base of 3. That's the first thing. And then I have this button over here on this particular calculator. To put in an exponent, you might have this button, a raised to a b. I have another graphing calculator here, and that button just looks like this. And that's called the caret. So either of these options will put our number up into an exponent. I think on the iPhone, it might actually be even a different button. Let's see. It looks like this, x raised to a y. That way, when you push that button, you're telling it, okay, I'm going up into the exponent now, and then you can type in what your exponent is going to be. So over here in our graphing calculator, I've typed 3 as my base, and now I'm going to press that A raised to a B button, and you can see it moved it up into the exponent spot. I'm going to type my exponent, 2.133. And the cool thing about this calculator is it's calculating as I type. You can see that my number changed as I typed it because the more specific you get in your exponent, the more specific an answer you're going to get. So, since we're dealing with a number that probably isn't going to end, I'm going to type a squiggly equal sign. That means it's approximately. I'm giving an approximate answer. It's not an exact answer because it's not like I'm getting 5 or 1/2. I have 10.415967984 blah 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 blah. So it's an approximate answer. It's not an exact answer. We have this really cool symbol, the squiggly equals, that means approximately. So 3 raised to 2.133 power is approximately 10.415967984. It's approximately that. That's awesome. Okay, let's do another one. Let's do E. So I'm going to find my E here. E, which is our base, raised to, so I press that A raised to a B button again. It's raised to, I'm going to put negative 2.4. And there we go. We have our answer, approximately 0.0907179532894. Quite a lot. It goes on forever. Then our last one that it wants us to try is 4 raised to, I press that A raised to a B again, 4 raised to a square root of 3. Square root button, 3, and there we go. Approximately 11.035664636. There we go. We have some examples of how to evaluate exponential functions. There are definitely more examples in the text and also in your guided notes, and then plenty of resources to get more practice on putting these things in our calculators and getting out our approximate numbers. Let's continue. We're going to look at some graphs and how these different numbers that we were evaluating would affect a graph. So we would get all these different numbers, right? We had these bases, we had some positive numbers going in, some negative numbers, some square root numbers. How does that affect what the graph is doing? Well, we can get the case of an exponential growth where we see that it is growing, right? Exponential growth. And then we can also see cases where we have an exponential decay, or the amount of whatever we're talking about is decaying. Our function looks like this. F of x equals b raised to an x. And just like before, when I was talking about, I see my base is a b and my exponent is an x. So we still have that same idea of a base holding up our exponent. Now, x is any real number, b is greater than 0, and it cannot be 1. Okay, because if we just have a 1, that's just going to be a straight line at 1. So b is a number greater than 0, and x is any real number. How do we get these growths and these decay functions? Well, that's where we get really specific about our b. So if it's a decay function, that means that our b value, the base, is somewhere in between 0 and 1. So a fraction of some sort. That's going to cause our amount to decay. Then if b is greater than 1, well, that's going to cause our amount to grow. You can think of that as an exponent, right? Exponent tells us multiply this number by itself over and over and over. So if we have a fraction and we're multiplying it by itself over and over and over, then of course we can expect it to be getting smaller and smaller and smaller. And if it's a number that's greater than 1, multiplying it by itself over and over and over, we can expect it to be getting bigger and bigger and bigger. And just by looking at this graph, it's getting big really quick, right? Think of multiplying a number, 5 times 5 times 5 times 5. That's going to grow really big, really fast. So that's our introduction to our growths and decays. Now, along those same lines, we can see when our slope is increasing, right, it's going in that upward direction. And this example down here also shows our slope is increasing. So both of these examples are when our slope is increasing. The big difference here is one of them has a positive intercept and one of them has a negative intercept. Okay, we can see the same idea over here, decreasing slope, right? We can see our slope is going down in both of these cases, but we have a positive intercept and a negative intercept. So our graph can be up above that x-axis, it could be below our x-axis. It's not going to change the fact that it's either growing or decaying. Some of the transformations we're going to see in all the functions we work with throughout this whole entire course are the basic transformations on functions. So if I add something to my function, it's moving it up. If I subtract something from my function, it's moving it down. If I'm adding to my input, if I'm adding to that x value, that's moving it left. And if I'm subtracting from it, that's moving it right. So we're thinking way back to our algebra skills where if I'm adding and subtracting, it's moving it up and down, or it's moving it left and right. If I take the negative of it, it's reflecting it. So it's either going to reflect it over the x or it's reflecting it over the y. Depends on where is that negative coming from, right? Also, we'll see stretching and compressing. So if it's multiplying times our function and it's a number that's greater than 1, it's going to stretch it out. We're going to see it really big. And if it's a fraction, it's going to be shrinking it down or compressing it. Same thing with horizontal, right? We can see it stretching vertically or horizontally. We can see it compressing vertically or horizontally. Both of these things are an option. So these are all a really quick review of transformations. We're going to see these same transformations happening on our exponents. Let's see some examples. Let me give you some examples. Here we can see if g of x is 2x plus 3, f of x is 2 raised to the x, and h of x is 2 raised to x minus 3. These are 3 different examples. We've got our kind of our parent function is what we would call it, of 2 raised to the x. So that's the OG, that's original guy. 2 raised to the x is our parent function here. Then we're going to say, I wonder what happens if maybe I subtracted 3 from that exponent. Well, we can see that it went ahead and moved it over. So subtracting on our x moved it over. And then we can see the same thing happening. Oh, I wonder what happens if I add to the x this time. Then I can see it moving over the other direction. So either way is affecting it. And if we go back to those transformation rules, we can see it right there. It tells us, oh yeah, it was gonna move it horizontally. And if I'm adding, it's moving to the left. If I'm subtracting, it's moving to the right. So that all comes together in a perfect circle to show us the transformations happening in real life. Here's another example. This example, we see, okay, here's my parent function, right? 2 to the x. And if you're thinking, what is parent function? What does that mean? I'm just looking at the basic exponential function, 2 to the x. We're not adding to it, subtracting, multiplying. Nothing's happening to it. It's just an exponent on a base. So then that's my parent function. That's what I consider like the norm. What happens if I add 3 to the whole thing? 2 raised to the x plus a 3. Well, look at what happened. It moved the function up. The whole thing went from orange to blue. It moved the whole thing up 3. What happens if I subtract the whole thing by 3, right? I can see it's subtracting by 3. Well, what would we guess? We would guess that it would be moving it down by 3. And from the orange one to the red one, that's exactly what happened. It moved it down by 3. So these transformations, right? We saw that in our table up here, that if I add to the function, it moves it up. And if I subtract from the function, it moves it down. And that's exactly what we're seeing here in our graph. So it's beautiful. It's beautiful to see those working together. Here's another example, reflecting. If I have my parent function, f of x is 2 to the x. I did not plan all these to be just the same 2 to the x, but it's really awesome that that happened. What happens if I make it a negative version? Well, I'm going to see it reflect. So it's reflecting over my x-axis here. It's an exact reflection, like if it's looking in a pond and it sees itself. What happens if we only make the exponent negative? Well, it's reflecting over the y now. It's looking at itself in a mirror. It reflected it over. So those are perfect examples of reflecting it. Now, you might be thinking, would we ever see more than one happen in the same function? And the answer is yes. Here we have a different parent function, 4 raised to the x. 4 to the x is our exponent function. Well, what transformations are happening over here? We have x plus 2, and then the whole thing is plus 1. So what do these transformations tell us? Let's break it down one at a time. First, we see x is being added by 2. That tells us it's moving to the left by 2 units. So everything has moved over by 2. What does this plus 1 on the whole thing tell us? Well, it tells us that everything moved up by 1 unit. So anytime we see something, it moved over 1, 2, and it moved up 1. So that's where the new thing is. And everywhere, that happened everywhere. Everywhere. So the whole thing moved over 2 and up 1. The whole thing. That's what those transformations are telling us happened to this particular function. And that's how the transformations are going to work. We're going to start with some sort of parent function, the general exponential, and see what happens to it if we start doing these transformations. So that brings us to our second objective, graph exponential functions. Graph the following functions and determine the domain, the range, the asymptote. So when we're looking at these graphs, first we're going to graph it. And then we're going to start talking about, okay, what's the domain? Domain is all of our x's, all possible x values. So what are all the numbers that we could possibly plug into the function? What is our range? Well, our range is going to be all the possible y values. All the possible y values. all of the values that we could possibly get out of the function, all of the outputs. And then our horizontal asymptote, that's a fun one. That is just the line, the horizontal line that the exponential will never cross. So if this, for example, was our exponential function, this dotted line right here is our horizontal asymptote. So we would just say, oh, the horizontal asymptote is y equals 0, or, you know, whatever that happens to be. So let's look at some examples. We're going to go over 2 specific examples and talk about these things. Our first one is y equals 4 raised to x minus 2, and the whole thing minus 2. Let's start by looking at what we think is going to happen. 4 raised to the x. That's our parent function right there. 4 to the x power. What would we expect? Well, 4 is greater than 1, so I would expect exponential growth. Then we've got, and let me put an axis on here. I would expect, well, the whole thing's being subtracted by 2, so that means that everything's going to be moved over by 2 units. And then, oh, no. This one, the whole thing is being subtracted by 2, so the whole thing is going to be moved down by 2 units. There we go. Then I see over here, let's get a pink, I guess. My x is being subtracted by 2, and when we subtract it by 2, that tells us we're moving to the right 2 units. So let me make that even better. We would move down 2, and we would move to the right by 2. And that should tell us, okay, if this point's moving here, and this point moves down and over, and this point moves down and over, then we're gonna get something that looks, maybe it looks like this. That's what we expect. Let's find out how close we are, okay? So let's get that graph back up. Let's graph these things. We want to see 4 to the power of x minus 2. Whoop. We're still in the power. Get up there. Minus. Oh, okay. This is a good lesson. Because we have more than one thing happening in that exponent, let's put parentheses. That way the calculator knows we are still up there. It's not just an x up there, it's an x minus 2 that's up there, and it's really important for us to tell the calculator that. A lot of calculators will only do what you tell them, exactly what you tell them. So if you don't put a parentheses around it, it's not gonna keep it up there. And then we have the whole thing minus 2. All right, and you know what? Just for comparison, I also want to put up the original 4 to the x. Okay, so the original is in orange, and the transformations are in black. So we see our original 4 to the x, and then we see our transformed function, and looky there, it has moved down and to the right, just like we expected it to. How awesome is that? Okay, so now let's talk about some other things. We want to talk about what is our domain. Our domain is how far does it span on the x-axis. We can look, well, it's going forever in the negative x direction. So when I would write the domain, I'm going to put domain, and it goes to negative infinity all the way to, and it just keeps going. I mean, it's slowly moving. It's slowly moving to the right, but it's going forever, so it's not gonna stop. Negative infinity to infinity. That's our domain. We can plug in any x value and it'll give us some kind of a number. Might be really, really huge, but it'll still give us something. Now, what is our range? Well, our range is going to work a little different because what's the smallest number we can plug in? It looks like negative 1.9, negative 2, it looks like it's getting closer and closer and closer to that negative 2, and it's probably never going to go any lower. So we're going to say it goes to negative 2, and it goes all the way up. I mean, that's not going to stop, so it's going to go all the way up to infinity. Our y values, our range, goes from negative 2 all the way up to positive infinity. And then we're going to talk about our horizontal asymptote. So remember, where is that horizontal line, that invisible line going along the horizontal that it's never going to cross? Well, we saw that happening right there at that negative 2. It's never going to cross it. So our horizontal asymptote is at y equals negative 2. That's where it's never going to cross. Never going to go across that negative 2. We're never going to have a y value at negative 6 or negative 4. Nope, it's just going to get closer and closer and closer and closer to negative 2. It's in love with it. It wants to be there, but it'll never reach it, sadly. Let's do another one. Okay, I'm going to clear this one out. The next one is 3 minus e to the negative x. So what do we think? So first, our parent function, e to the x, right? Parent function, e to the x, goes through at 1. What do we expect it to look like? Well, we can see that there's a negative there, so it's going to be reflecting it. We see a 3 added to it, so it's going to be moving up. We can see that our x is reflected, so both reflected over the x and the y. It's reflected over both. So let's see what that'd look like. Reflect over the y value. Let's see, I'm gonna have to do it in 2 parts because I cannot picture it in my head. If I reflect over the y, then it's gonna look something like this. And then if I take that and reflect it over the x, it's gonna look something like this. So after we do that, and then we add 3, I want my pink one to be what we expect. So here's the reflected one, and then the pink one. If we move it up by 3, we expect it to be something like this. Not to scale. Let's see what it actually looks like. So we have 3 minus e, let's find our e, raised to, put out parentheses, a negative x. Where are you? There you are. And there we go. We've got this guy. Let's get that out of the way. Let's get some important information down about our graph here, our domain. What are our x values? They are going from negative infinity to infinity. We can use any x value that we want. What is our range? Well, it goes to negative infinity and all the way up to, looks like 3. It looks like it's going to 3. And that makes it really easy for us to label our horizontal asymptote because our horizontal asymptote is going to be y equals 3. I really hope that these examples were able to give you a really good idea of what's happening in these exponential functions, what we're looking at, what is affecting them as they transform into these other functions. Of course, you can look at many more examples in the book and on YouTube on how these transformations affect our graph. Some of the really big takeaways is understanding what my domain is, that's my x's, what my range is, that's my y's, and then that horizontal asymptote is along the horizontal. Where is the graph stopping? Where is that invisible line that it's not going to cross over? One question that may come up is there also ever a vertical asymptote? And that's a really good question. In these cases, we haven't seen one, right? We've seen that they're just expanding along the x's all the way. In graphs in the future, we will see horizontal asymptotes, vertical asymptotes. There's even the possibility of graphs that have asymptotes across a line. So maybe they have an asymptote where they can't cross it on the y equals 1 or y equals x line. That's further into the course right now. Just focus on your exponentials and you'll be fine. Let's go back to our notes here. Exponential functions are written as a base raised to an exponent, and our base is greater than 0 and it's not 1. Remember that whatever our base is going to affect our graph. So if our base is greater than 1, we're seeing that exponential growth. And when our base is a fraction, we're seeing that exponential decay. This is a really nice note page of the domains, the ranges, even the y-intercepts of these general functions. But the horizontal asymptote, all these things that we are studying in our course, and it's laid out for us in our general form right here. Okay, now we saw e, right, as a base to one of those functions we looked at earlier. So I kind of want to focus on e a little bit, give it some love. The number e is extremely important in mathematics. It's one of the most important numbers. It was developed by a mathematician named Euler, and this is the definition of what e is. So if we take 1 plus 1 over n and raise it to the nth power, and we just add that when n equals 1, and then we add that when n equals 2, we plug these things in and we add that to n equals 3, what happens? Where is this going? Well, it's going to show us e. And so what we do is we take the limit as n goes to infinity, so we're adding all of these things up. As it goes to infinity, we can see that e is somewhere around 2.7182818284559, blah, 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 blah. It goes on just like pi, but it's getting closer and closer to this 2.7 number, and that number is e. And e is really cool because it happens so many times. It keeps appearing in nature, and mathematicians were really drawn to it because it kept coming up, and once they were able to figure out what e was, this approximate number, and that it was solving all of these things and fitting into all of these approaches, it was really beautiful. So mathematicians get excited about e because we see it, and it's able to give us the opportunity to model what we see happening in the world, in nature, in mathematics. We're able to model it in mathematics using e. So that's the importance of it, and this is the definition of it. I'll go back up to it, is this right here. This is our definition of what E is, but this is our approximation of it down here. This is our little approximation of what E is, if you were ever wondering, why are we using a letter? Well, it's because one, it never ends, and two, to be honest, they ran out of symbols, so we started using letters, to the short answer for that. Okay, moving right along, our exponential function can have a growth factor or a decay factor. So let's take a look a little bit closer at our function itself. Remember, our base tells us if it's an exponential growth or an exponential decay, which means that's telling us what our growth and decay factors are. So down here we can see our growth factor of 1.25. That's our base. 1.25 is the base. That's telling us it's a growth factor, because remember, it's greater than 1. Down here we have 0.97, and that's less than 1, so it's telling us that's a decay, so that's our decay factor. Now, what is this number out front? We have this number out front multiplying times it. That actually tells us our, I guess I didn't write it down. That tells us our initial value. So, for example, this is a growth. This is a growth example. Population. Let's say, since we started with 50, we're dealing with rabbits, the rabbit population in a certain little country town. They logged that there were 50 rabbits, and they were able to calculate that the growth rate of these rabbits, the growth factor is 1.25. So after so many amount of time, let's say 1.25, let's say that it's a daily. So every day they're growing by 0.25, so 25% growth. So this is telling us that the population's growing by 25%. It started at 50. Okay, that's just our real world example. For decay, we could say that we'll use chemistry maybe, and say we have this element and we started with 2 grams of our element, and as it has been exposed to the air, the decay that it's experiencing is 0.97. So it is decaying by 3%. We're losing 3% of it every hour. Maybe it's dry ice or something sitting out, and it's decaying at a certain rate. So we can see that these things become very important. These rates and these initial values and the use of exponentials is very important in calculating some of our real world issues we're experiencing. Here's another example. If we have exponential growth, what is our domain? It's from negative infinity to infinity. And then what's our range? From 0 to infinity. Now, this is all information based off of our original parent function. So as we experience those transformations, remember we have to account for those as well. Some of the important things that I want to draw your attention to are the y-intercept, because that's our initial value. Okay? When you're graphing these things and you're looking at what's the initial value, you're going to be looking for that y-intercept. Some other things, the end behavior. That's going to tell us if it's going to positive infinity, if it's going to a number like 0. That's what's happening on the ends of our graph. And those are important for us to notice, because then we'll be able to see what are our asymptotes. And And then our final objective for today is solving exponential equations. These are so much fun. I think they're so much fun personally because it's almost like figuring out a puzzle. Here we have solve each equation, and then we have two problems that we're going to do together. The first one, 2 to the 3x power equals 4 to the x plus 1 power. So, what do we know about exponentials that can help us solve this problem? Well, what I know is if my bases are the same and they're equal, that means the exponents have to be the same too. So that's what I'm going to use to solve this problem. And I'm going to write it on the side because it's really important. It's an important thought. If my bases are the same, and the two quantities are equal, then the exponents have to be the same too. Okay, so let's get to solving and let's use this idea. If my bases are the same, okay, record scratch, my bases are not the same, but can we make them the same? And the answer is yes, yes we can, because I can turn 4 into a number with a base of 2, right? How can we rewrite 4? Well, 4 is just 2 squared. And then that exponent stays the same. We didn't do anything to the exponent. We just changed the 4. We rewrote it as 2 to the second power. Okay? So now that we have bases are the same, that means that we can begin to solve it. All we have to do is make sure that our exponents are the same. That taking that idea, I need to make sure that the exponents are the same. So that's all we're going to do, is we're going to make sure that our exponents are the same. I'm going to look at my exponents. 3x must be equal to 2x plus 1. They must be. That's the only way that these two quantities are going to be equal, is if the bases are the same and the exponents are the same. So now I have a problem where I can just solve for x. The first thing I'm going to do is I'm going to distribute. So I've got 3x equals 2x plus 2. And then I'm going to subtract my 2x to the other side, which leaves me with x equals 2. And there you go, you solved it. The last thing that I would do is I would double check it. I would like to check my answer just to make sure that it's good. So 2 raised to 3 times 2 equals 4 raised to the 2 plus 1. So I have 2 raised to a 6 power equals 4 raised to a 3 power. So 2 to the 6th, what do we got here? Two to the 6th power, 64, and 4 to the 3rd power, 64. So it checks out, and we're good to go. Always good to double check, make sure that the answer you get is, if you can check your answer, I mean, why not, right? All right, let's do another one. Here we have base of e, beautiful little e. Okay, e to the x squared equals e to the 3x minus 2. Now remember, bases are the same. That means exponents also need to be the same in order for these two quantities to be equal. This one is really nice because our bases are already the same. So this means that our exponents need to be the same. So x squared equals 3x plus 2. Well, let's solve for x again. Now this one is a little bit more interesting, right? Because we have an x squared. So here's what we're going to do. I'm going to say x squared minus 3x plus 2 equals 0. So what did I do? I'm sorry, I jumped the gun here. I am going to move these things to the other side. So after I move those two things to the other side of the equation, I have x squared minus 3x plus 2 equals 0. And now I can reach way back into my algebra skills and factor this. So I've got x, a 3 and a 1, and plus 3 minus 1. If you need a review factoring, go ahead and go find some review practice of factoring. Now that we have this, we can solve. So x equals negative 3 and x equals 1. And that is going to be it. We have two answers for this. 2 times 2 different x's would make these quantities equal. So we could write this as a set. So in set notation, we would have negative 3 and 1. Okay? And that is our notes for today. We've accomplished all of our learning objectives in these examples, went over brief notes, and I expect that you will also complete your guided notes with the text to get a really in-depth coverage of that.